Okay, picture this. A material so incredibly thin, it's just one atom thick. It's also the strongest stuff ever measured, well, on a microscopic scale anyway. It won a Nobel Prize, and get this, you can isolate it using nothing more than sticky tape. Sounds like science fiction, doesn't it?
It really does, but surprisingly, it's very much real.
Absolutely. Welcome to the Deep Dive. Today, we're taking a deep plunge into the world of this remarkable material, graphene.
Right, it's a fascinating form of carbon.
Exactly. And we've pulled together source material, specifically key excerpts from the Wikipedia article on graphene, to unpack its incredible story, its truly mind-bending properties, how researchers actually make it, and, where it's already starting to show up or could completely transform technology in the future.
Our goal here is really to guide you through this information, pulling out the most important insights and facts. We want to give you a clear understanding of why graphene is considered, well, revolutionary, basically providing you with a shortcut to being well-informed about it.
Okay, so where does the story of graphene even begin? Because this wasn't just some spontaneous discovery in 2004.
Oh, not at all, no. The idea of a single, stable layer of carbon atoms arranged in that honeycomb structure actually goes back decades. Philip R. Wallace first theorized its existence way back in 1947.
Wow, 47.
Yeah, while he was studying the electronic behavior of graphite, pencil lead.
So the theoretical concept was out there just floating around for a long time.
Pretty much. And the name graphene itself, that was defined much later, 1987, by Hans Peter Bohm. He was also looking at thin layers of graphite. I mean, people had even seen images of thin graphite layers in electron microscopes way earlier, even back in the late 1940s. The challenge wasn't just seeing it, it was isolating a single, stable layer and proving it had unique properties.
Right, because graphite, like you said, pencil lead is just stacks and stacks of these layers. Getting down to just one must have been incredibly difficult.
It really was. There were attempts, to grow thin layers on other materials back in the 70s, but those layers often interacted too strongly with the base material, changing their properties.
Ah, okay.
And people tried mechanical peeling in the 90s, getting down to maybe a few layers thick, but a single layer? It just seemed impossible to handle, too flimsy.
Okay, so the stage was set, the theoretical idea was known, people had seen thin layers, but isolating one perfect sheet was the holy grail. And then came the moment that changed everything.
Yes, the breakthrough that really kicked off this current era of intense research was in 2004. That's when Andrei Geim and Konstantin Novoselov at the University of Manchester finally managed to isolate and characterize single-layer graphene.
And how did they do it? This is where the legendary sticky tape comes in.
Precisely. Their method, which sounds almost unbelievably simple, involved using, a piece of standard adhesive tape like Scotch tape and a piece of graphite.
Just like that.
Pretty much. They'd stick the tape to the graphite, peel it off, getting some layers, and then stick that piece of tape onto a silicon wafer coated with a thin layer of silicon dioxide.
They were just peeling off layers, like shedding skin.
Essentially, yeah. They repeated this process, transferring thinner and thinner flakes onto the silicon wafer, and that silicon dioxide layer was key.
Why was that?
Well, it provided a surface that the graphene stuck to, but it didn't strongly interact with it chemically or electronically. So the graphene could behave more like a pristine, isolated sheet, and the silicon underneath, you could even use that to apply a voltage, sort of like a switch, a gate.
It is honestly astounding that such a low-tech, almost accidental-sounding method led to such a profound scientific discovery.
It truly is a fantastic story. Simple ingenuity leading to a huge breakthrough. And the scientific community, they recognized its significance almost immediately. This groundbreaking work earned Geim and Novoselov the Nobel Prize in Physics in 2010.
And after that Nobel, what happened then?
Well, their publication, and especially how accessible their method seemed, sparked what's been called a graphene gold rush, just an explosion of research.
Right.
Researchers worldwide just jumped in, exploring every conceivable property, mechanical, electronic, thermal, optical, chemical, biological, you name it.
So everyone wanted a piece of the action.
Absolutely. Now, scaling up that original sticky tape method for, mass production, that's still a challenge for big industrial applications. But the discovery itself, it just opened up this vast new frontier in material science.
Okay, so let's get down to the basics then. What exactly is this material they isolated? Describe the structure for us.
Okay, at its most fundamental, Graphene is just a single layer of carbon atoms.
Just one atom thick. That's almost hard to picture properly.
It is. And these carbon atoms, they're arranged in a perfectly flat, repeating hexagonal pattern, like think of chicken wire or a honeycomb lattice, but at the atomic scale.
So chemically, it's just pure carbon. The formula is just C.
Correct. And the name comes from graphite, which is those stacked layers plus the suffix IIN, which chemists use to indicate double bonds, which, are part of the graphene structure.
And being just one atom thick makes it, by definition, the thinnest material possible in 2 dimensions, right?
Exactly. Its measured thickness is really consistent with the distance between layers in bulk graphite, about 3.7 angstroms. Very, very thin.
How can you even see something that thin? If I held up a piece, would I actually see it?
This is one of the really surprising facts from the source material. A suspended single-layer graphene membrane can actually be seen with the naked eye.
Wait, really? How?
Even being just one atom thick, it absorbs about 2.3% of visible light that passes through it.
Hold on, that seems completely counterintuitive. Graphite, which is thick stacks of this stuff, is black because it absorbs pretty much all the light.
Right, it's weird. And a single layer absorbs just this tiny but consistent amount across the whole visible spectrum. That unique interaction with light is actually one of its special electronic properties.
Okay, we know the history, the structure. Now let's get to the really exciting part, the properties. Why is this single sheet of carbon considered so revolutionary? Let's start with its physical and mechanical properties. Strength, stiffness, that kind of thing.
Okay, this is where the numbers start sounding, well, a bit like science fiction. Graphene has an exceptionally high tensile strength. That's its resistance to being pulled apart. We're talking around 130 gigapascals. GPa.
130 GPa. Put that in perspective for us. What does that compare to?
Well, that's about 200 times stronger than typical structural steel. And on a microscopic scale, it's actually the strongest material ever measured. Period.
Wow.
It also has a very high Young's modulus, which is a measure of its stiffness, around 1 terapascal. That's TPa. Also incredibly high.
Okay, so incredibly strong, incredibly stiff, and yet its density must be incredibly low, right, being so thin.
Precisely. Its 2D density is just 0.763 milligrams per square meter. Think about it, the strongest material ever measured at this scale, and it's impossibly thin and light.
That combination of strength and thinness is just mind-blowing.
Is it rigid, though, or can it bend?
Despite its stiffness, it's remarkably flexible and robust. It can undergo large-angle bending without breaking, apparently, and still maintain its excellent electrical properties.
You mentioned it's perfectly flat, but I seem to recall reading something about it not being entirely flat in reality.
You're right. While the ideal structure is flat, single sheets are actually theoretically unstable to scrolling, meaning they kind of want to curl up. And researchers have observed tiny ripples in suspended graphene layers using advanced microscopes like TEM or STM. These ripples are tiny, about 1 nanometer in amplitude.
Why the ripples? Is it just flimsy? Or something else?
The exact reason is still debated. It might be an intrinsic behavior of these perfect 2D crystals, a fundamental instability. Or it could be caused by external factors like tiny bits of dirt or just conforming to the surface it's resting on.
Okay.
But here's where it gets really weird. If defects in the graphene amplify these ripples, they can actually induce what's called a negative Poisson's ratio. A negative Poisson's ratio, isn't that where if you pull on something, it gets wider instead of narrower?
Exactly. Most materials get thinner when you stretch them. Auxetic materials, which graphene can sometimes be due to these ripples, get fatter when pulled. Graphene is the thinnest known material to potentially exhibit this very strange property.
That's wild. Okay, so strong, stiff, flexible, incredibly light, potentially auxetic. But is it tough? Or does it crack easily?
Good question. Despite its incredible strength, it's actually relatively brittle, meaning it tends to crack rather than deform plastically like metals do. Its fracture toughness is more similar to ceramics. So yeah, imperfect graphene can be fragile in that sense.
Okay, strong, but maybe not tough everywhere. Depends on defects. What about impact? I saw something mentioned about its impact resistance.
Yes, studies have shown graphene has this exceptional ability to distribute force from an impact very quickly. It can transmit that force at something like 22 kilometers per second.
Whoa.
Which is like 10 times faster than steel per unit weight. So it handles shock really well.
Wow. So it can handle impact shock incredibly well, efficiently spreading the force. What about larger pieces of graphene, like the ones made by growing it? Are they different from those tiny Nobel Prize flakes?
Yes, definitely. When you make larger sheets, especially with methods like chemical vapor deposition or CVD, they often aren't perfect single crystals. They are polycrystalline, meaning they're made of many smaller crystal grains joined together at grain boundaries. And these boundaries usually contain defects, like arrangements of 5 and 7 carbon rings instead of the usual perfect hexagons.
And how do these boundaries affect the strength? Does it make it weaker?
Well, this is a complex area. There's ongoing research and even some debate. Some theories suggested strength could depend on the angle where the grains meet, or even how big the individual grains are.
Right.
But the studies mentioned in the source material give conflicting results. Some find larger grains make it stronger, some find smaller grains make it stronger, which is kind of the opposite effect, and others find little effect at all. It seems the specific arrangement and the nature of the defects at those boundaries matter a lot more than just, say, the average grain size.
So the way you make it and the imperfections introduced during scaling up really influence its final mechanical properties. It's not straightforward.
Absolutely. It really highlights the challenge of translating those amazing lab-scale properties to large-scale, real-world applications. You need consistency.
All right, that covers the physical side. Now let's talk about the electronic properties, because this is really what first got physicists so incredibly excited, right?
Indeed. Graphene is classified as a zero-gap semiconductor, or sometimes called a semi-metal.
Okay, what does that actually mean for someone who isn't a physicist? Like, break that down.
Okay, think of traditional semiconductors, like silicon and computer chips. They have a clear energy barrier, a band gap, that electrons have to jump over to move freely and conduct electricity.
Right.
In graphene, that barrier basically disappears. The energy bands where electrons are allowed to be the valence and conduction bands they touch at specific points, these are called the Dirac points. And this meeting point gives rise to some incredibly unusual electronic behavior.
And I've had terms thrown around like massless Dirac fermions. Sounds very exotic.
Yes, this is the really cool part. Scientifically, electrons moving through graphene near these Dirac points behave as if they have no mass. They don't follow the usual rules for electrons in metals or semiconductors.
No mass.
Their behavior is described by a physics equation, a 2D version of the Dirac equation, which is normally used for relativistic particles moving near the speed of light. So they act almost like particles of light, photons, but they carry charge. They're effectively massless in how they move through the lattice.
So they zip around incredibly fast and lightly, without much resistance.
Exactly. And this led directly to the observation of some really bizarre quantum phenomena early on.
Like the quantum Hall effect you mentioned?
Yes, but an anomalous version of it.
Mm-hmm.
In 2005, Games Group, and independently Philip Kim and Yuanbo Zhang, observed this strange quantum Hall effect in graphene they'd made with the sticky tape method.
How is it anomalous or strange?
Well, normally, when you apply a strong magnetic field to a 2D conductor, the electrical resistance changes in standard whole number steps. In graphene, they saw half-integer steps.
Half-integer steps. That's definitely not normal.
No, and it was direct experimental proof that the electrons in graphene were behaving like these predicted massless Dirac fermions. It was a huge validation of a theory, a really big deal in physics.
Oh, wow.
And interestingly, even bilayer graphene, just 2 layers stacked together, shows a slightly different but also anomalous version of the quantum Hall effect. It might even be metallic right at the neutral point.
So even adding just one more atomic layer fundamentally changes the quantum behavior.
It does. It just demonstrates how incredibly sensitive the electronic properties are to the number of layers and exactly how they're stacked.
Okay, strange quantum behavior aside, just how well do charges actually move through it? Is it a good conductor in practical terms?
Oh, it's an excellent conductor. Graphene has exceptionally high electron mobility at room temperature. Values reported were over 15,000 centimeter sotavis early on.
And mobility means?
High mobility means electrons can move very freely for long distances without bumping into things or scattering. And unlike many materials, both charge carriers, electrons, and the holes they leave behind move with nearly the same high mobility.
That's useful.
Very. And this mobility stays high even as temperature increases, which suggests that most of the scattering, the stuff limiting the movement, comes from defects in the graphene itself or interaction with the substrate it's sitting on, not from the graphene's own vibrations, the phonons.
So the graphene itself is almost perfectly conductive.
The theoretical limit for perfectly clean, suspended graphene is much, much higher, potentially over 200,000 centimeter positions. But putting it on a substrate like silicon dioxide limits it to maybe around 40,000, and even tiny bits of leftover chemicals from processing can drop it further.
So getting those super high mobility numbers in practice requires incredibly pristine graphene and careful handling.
It absolutely does. And in terms of resistance, graphene has extremely low resistivity, around 10 ohm-meters.
How low is that compared to, say, metals?
That's actually lower than silver, which is typically considered the best electrical conductor at room temperature.
Lower than silver. That's remarkable.
It is, though there are challenges, of course. Charge transport can be affected by contaminants from the air like water and oxygen. They can stick to the surface and cause issues like hysteresis in measurements where the reading depends on past conditions.
Ah, so it can be unstable.
It can be. That's why often sensitive experiments are done in a vacuum. Or researchers use protective layers made of other materials, like silicon nitride or boron nitride, to shield the graphene from the environment.
Okay. And I saw a note about superconductivity. Can it be superconducting?
Yes, although not on its own, typically. In 2015, researchers showed that if you coat graphene with lithium atoms, it could become superconducting at low temperatures. That was the first time superconductivity had been observed in graphene in any form.
So it can go from being one of the best normal conductors to a superconductor under the right conditions? What about the way current flows? Is it just like electrons bumping along in a normal wire?
Not always, and this is another fascinating aspect. Electrons in high-quality graphene can travel for micrometer distances without scattering at all, even at room temperature. This is called ballistic transport.
Ballistic, like little bullets.
Exactly. Instead of bouncing around randomly like in a typical conductor, diffusive transport, they travel in straight lines like little projectiles. And in very narrow strips of graphene, called nanoribbons, the transport can depend on the length, sometimes ballistic, sometimes hopping between localized states.
That's fascinating. It sounds like the fundamental rules of electron movement are just different in graphene.
They really are in many ways.
Yeah.
And there's still a puzzling aspect called minimum conductivity. Even when you tune the voltage so there should be theoretically zero charge carriers available to conduct, right near that Dirac point, graphene still shows a measurable minimum level of conductivity.
Why would that happen if there are no carriers?
The exact reason isn't fully settled. Theories suggest it might be due to those ripples we talked about, the unevenness of the sheet, or perhaps tiny localized puddles of charge caused by impurities in the underlying substrate that allow some conduction even at the neutrality point. It's still an area of active research.
Okay, so lots of weird and wonderful electronic stuff. Any other cool electronic or magnetic behaviors?
Well, there's the potential to actually give electrons mass in graphene. If you place graphene on another specific 2D material, hexagonal boron nitride, HBN, it can slightly alter the potential experienced by electrons on the two different carbon sites in the honeycomb lattice.
And that gives them mass.
Effectively, yes. It opens up a small band gap around 30 millielectron volts, and the electrons start behaving as if they have mass. What's really interesting is that this induced mass can be positive or negative depending on the alignment.
Positive or negative mass.
Yeah. And if you could pattern regions with positive and negative mass next to each other, the boundaries between them could host special conducting states, similar to what happens in topological insulators. Electrons could potentially flow along these boundaries without scattering, leading to dissipationless current.
Wow, that sounds like a path towards ultra-efficient electronics.
It's a very exciting theoretical possibility, yes. It suggests you could potentially confine electrons in massless regions surrounded by massive regions, creating quantum dots or wires where transport is protected.
Incredible potential there. Okay, let's move from electrons to light. Optical properties. You mentioned it absorbs that small 2.3% of light, which is weird. What else is unique about how it interacts with light?
Right, that small, constant absorption across the visible and infrared spectrum is quite unique for a single atomic layer. It's a direct result of its unusual electronic structure, those conical bands meeting at the Dirac point.
Okay.
But beyond just absorption, graphene can support something called surface plasmons.
Plasmons, what are those?
They're like tiny collective waves of electrons oscillating on the surface, coupled to light. Think of them like ripples, but made of charge density waves that interact strongly with electromagnetic fields.
Okay. And what's special about them in graphene?
What's really cool is that in graphene, you can potentially control the direction of these plasmons, and you can tune their frequency over a huge range from very low terahertz frequencies all the way up to visible light frequencies just by changing the voltage applied to the graphene or by doping it.
So it could be used to guide or manipulate light waves at the nanoscale, like tiny optical circuits.
Exactly. It opens up a lot of possibilities in nanophotonics and plasmonics. And the bandwidth for these plasmons can be much larger than in traditional metals because the effective mass of electrons in graphene is so small.
Interesting. Any other key optical properties?
Yes, another really important one is saturable absorption. This is a nonlinear optical effect.
Nonlinear.
Meaning its response depends on the intensity of the light hitting it. For saturable absorption, graphene's absorption of light actually decreases when the intensity of the incoming light gets very high, above a certain threshold.
So it becomes more transparent when you shine a really bright light on it.
Essentially, yes, for light within a certain wavelength range. And this happens across an incredibly broad spectrum, from visible light all the way down to microwave and terahertz frequencies.
What's that useful for?
This property is very useful for things like mode locking and ultra-fast lasers, helping to generate very short, intense pulses of light. And because it works over such a broad range and can potentially be tuned electrically by applying a voltage.
You could make a lens or a window that changes how much light it lets through just by flicking a switch, or control microwave signals.
That's the kind of potential it holds. It opens possibilities for tunable optical or microwave devices like absorbers, modulators, polarizers, maybe even new types of signal processing or broadband wireless communication components.
Wow. And one more optical effect.
It also exhibits a very large nonlinear Kerr effect. This means that intense laser light can change the refractive index of the graphene, which in turn changes the phase of light passing through it. The effect is much larger than in typical dielectric materials, suggesting potential for advanced nonlinear optics, maybe even generating light waves that hold their shape over long distances, called solitons.
Okay, so light does some weird things too. Shifting from light to heat. How does graphene conduct heat? Is it as good as it is with electricity?
It's an exceptional thermal conductor, possibly even better, relatively speaking. Early measurements on high-quality suspended graphene reported incredibly high thermal conductivity figures up to 5,300 watts per meter per Kelvin. That's MER.
5,300. How does that compare to other materials? Isn't diamond known as a great heat conductor?
Yes, diamond is excellent, but that 5,300 value is significantly higher even than diamond, and much higher than pyrolytic graphite, another good thermal conductor, which is around 2,000.
So potentially the best thermal conductor known.
At room temperature, for the suspended form, yes. However, just like with electronic properties, placing graphene on a substrate or introducing defects significantly reduces this number.
Ah, the real-world caveat again.
Exactly. More scalable graphene, like the stuff made with CVD, often shows lower, but still very high thermal conductivity, maybe in the range of 1,500 to 2,500 Yerman. And if you support graphene on a typical amorphous substrate like the silicon dioxide used in chips, the conductivity drops much further, maybe to around 500 or 600.
Why such a big drop?
Because a lot of the heat energy gets scattered away into the substrate material instead of staying in the graphene layer. Even leftover polymer residue from transferring the graphene can have a similar scattering effect.
So the super high number is for perfect suspended graphene, but even the real wind-supported graphene is still a very good heat conductor compared to most materials.
Yes, absolutely.
Right.
Even those lower numbers make it very promising for thermal management applications, like spreading heat away efficiently from hot spots in electronic components or batteries.
Okay, makes sense. What about its chemical properties? Is it very reactive or inert like graphite?
Graphene has a huge theoretical specific surface area, something like 2,630 square meters per gram. It's enormous.
Why is surface area important chemically?
Well, for chemical reactions, the surface is where everything happens. Graphene is unique because it's the only solid material where literally every single atom is on the surface, available for reaction from two sides, top and bottom.
Right, because it's just one layer.
Exactly. And the atoms right at the edges of a graphene sheet, or near defects, has special chemical reactivity compared to the atoms in the perfect flat plane. Graphene has the highest ratio of these reactive edge atoms of any form of carbon.
So does it react easily with things?
It reacts with oxygen at relatively low temperatures, apparently below 260 degrees C, and it burns at around 350 degrees C, which is quite low for a carbon material. It's often intentionally modified or functionalized by adding chemical groups containing oxygen or nitrogen to tailor its properties.
Is single-layer graphene more reactive than thicker sheets?
Yes. The source mentions that single-layer graphene is reported to be about 100 times more reactive than thicker multi-layer sheets, at least towards certain reactants like hydrogen atoms.
But I also read something about it being able to heal itself. That sounds counterintuitive if it's reactive.
Yes, that's another fascinating property. Graphene can actually self-repair holes in its structure under the right conditions. If it's exposed to carbon-containing molecules like hydrocarbons, or even just bombarded with pure carbon atoms, the atoms can apparently spontaneously arrange themselves into perfect hexagons, filling in the holes and repairing the sheet.
That's incredible. It can literally patch itself up at the atomic level. Okay, finally, let's touch on biological interactions. Can it interact safely with living cells or tissues? Is it biocompatible?
This is a really complex area, and the understanding is still incomplete. Its biocompatibility isn't a simple yes or no answer. It seems to depend heavily on factors like the exact size and shape of the graphene flakes, whether it's a single layer or multiple layers, its surface chemistry, what chemicals are attached to it, if any, and even the type of cell it's interacting with.
So it varies a lot. What have studies shown so far?
Some studies have definitely shown promising interactions. For example, research mentioned from Cambridge showed it could safely interact with neurons without damaging them. It's also been shown to encourage human mesenchymal stem cells to differentiate into bone cells, which suggests potential for tissue engineering or regenerative medicine.
Okay.
And its unique electronic properties make it very promising for building highly sensitive biosensors, perhaps for detecting biomarkers for diseases like cancer risk.
So there's definite potential for medical or biological applications.
Yes, but there's also a need for caution. Concerns have been raised as well. For example, some studies using graphene microsheets have shown that the sharp, jagged edges can potentially pierce or slice cell membranes, which could cause toxicity.
Right, those edges could be a problem.
Exactly. So the toxicology seems to vary a lot based on the form. Tiny nanoparticles might behave differently than larger sheets. While the potential is definitely there, really understanding the nuances of its form, size, surface chemistry, and how it interacts with different biological systems is crucial for developing safe and effective biological applications. It's not a magic bullet yet.
Got it. So promising, but needs careful design and more research.
Precisely.
Okay, we've talked a lot about the amazing properties of a single perfect graphene sheet. But you mentioned graphene isn't just that one thing. It exists in various forms and structures.
Absolutely. It's more like a family of materials. Beyond the single monolayer, you obviously have bilayer graphene, just two layers stacked together.
And that behaves differently.
Yes, as we touched on. It has slightly different electronic properties. It shows its own version of the anomalous quantum Hall effect. And very interestingly, it has the potential for a tunable band gap.
Tunable band gap.
Meaning you can actually open and close an energy gap, turning it from metallic into semiconducting, just by applying an electric field. This makes bilayer graphene really promising for certain types of nanoelectronics and optoelectronic devices. The way the two layers are stacked also matters whether they're perfectly aligned, Bernal stacked, or twisted relative to each other.
And what if the layers are just randomly stacked, not aligned?
That's generally called turbostratic graphene. The layers are misaligned, which weakens the electronic coupling between them. Importantly, this misaligned stacking often allows the individual layers to mostly retain their unique 2D electronic properties, which can be useful. They act more like independent single layers.
Can you stack graphene with other types of two-dimensional materials, not just more graphene?
Yes, and this is a huge and incredibly exciting area of research right now. It's called van der Waals heterostructures.
The van der Waals! Like the forces.
Exactly. You can stack different 2D materials, graphene, hexagonal boron nitride, which is an insulator, molybdenum disulfide, a semiconductor, and many others layer by atomic layer, like building with molecular Legos.
Then why would you do that?
Because it allows you to engineer entirely new materials with tailored properties that you can't get from the individual components. You can create functional superlattices, tunnel barriers, complex devices, basically building integrated circuits atom by atom. It's a whole new way to design materials and devices.
That's fascinating, designing materials layer by layer. What about smaller structures made out of graphene itself?
Right, you can pattern graphene into different shapes. For instance, you can make graphene nanoribbons, which are just narrow strips of graphene.
And their properties change.
Yes. Critically, their properties depend on the shape of their edges at the atomic level. Ribbons with zigzag-shaped edges are predicted to have different electronic and magnetic properties than those with armchair-shaped edges. Zigzag edges might be metallic and spin-polarized, useful for spintronics, while armchair edges can make the ribbon behave like a semiconductor with a band gap that depends on the ribbon's width.
So the edge shape dictates the behavior. And tiny dots, can you make those?
Yes, graphene quantum dots are tiny fragments, generally smaller than 100 nanometers across. At this incredibly small size, quantum confinement effects start to dominate their behavior, giving them entirely different optical and electronic properties compared to larger graphene sheets. They might fluoresce light, for example.
Okay. We also hear a lot about graphene oxide, or GGO. Is that the same thing as graphene?
No, graphene oxide, GO, is a chemically modified form. It's usually made by taking bulk graphite and reacting it very strongly with oxidizers, like in the Hummer's method. This process basically attaches lots of oxygen-containing functional groups like hydroxyls, epoxides, carboxyls, all over the carbon sheet.
And what does that do to the properties?
It changes them significantly. Graphene oxide is typically an electrical insulator or poor semiconductor, unlike pristine graphene. It's also hydrophilic, meaning it likes water, and it disperses well in water and some other solvents, making it much easier to process into films or composites using solution-based techniques. You can even make paper-like sheets from it.
Easier to handle, but less conductive. And you mentioned a strange property with water permeability earlier.
Yes, this is a really interesting paradox. While pristine graphene is hydrophobic and essentially impermeable to everything, even tiny helium atoms, membranes made from stacked graphene oxide sheets, can somehow allow water vapor and even liquid water to pass through remarkably freely, almost like networks of tiny capillaries, while blocking other liquids and gases.
That's really unexpected for a carbon material membrane. How?
The exact mechanism is still debated, but it's thought to involve water molecules moving through the spaces between the judo sheets, or perhaps through defects. This weird property is being heavily explored for water filtration, desalination, and separation applications.
Okay. And can you turn graphene oxide back into something more like graphene?
Yes, you can chemically or thermally reduce graphene oxide to remove most of those oxygen groups. This creates what's called reduced graphene oxide, or RGO.
And that restores the conductivity.
It helps restore some of the electrical conductivity, yes, making it semiconducting or somewhat metallic again, although usually not quite back to the level of pristine, defect-free graphene, because the reduction process isn't perfect and can leave behind defects or residual oxygen. There are various ways to make RGO, like heating it, using chemicals like hydrazine, or even, as mentioned in the source, just burning a GO-coated DVD in a LightScribe drive.
Burning a DVD, seriously?
Apparently so. It produces a conductive RGO film. There are also hydrothermal methods, sometimes using sugar, that can produce stable suspensions of RGO in water.
Okay, so we have different forms: single layers, bilayers, turbostratic stacks, heterostructures with other materials, nanoribbons, quantum dots, and modified versions like GGO and RGO. What about making larger three-dimensional structures out of graphene?
Yes, this is another very active area of development. You can create graphene fibers, for instance.
Fibers, like thread.
Exactly. These are typically made either by assembling graphene oxide flakes into fibers and then reducing them, or sometimes by processing CVD-grown graphene films. These fibers can be strong, lightweight, flexible, and electrically conductive.
What could you use them for?
Well, they could be woven into functional textiles,
Yeah.
used as conductive wires in flexible electronics, or used as electrodes in things like supercapacitors or batteries. Some methods have even produced kilometer-scale graphene fibers, potentially for lightweight structural composites or advanced cables.
Like high-tech conductive thread. What else in 3D?
You can also make self-supporting 3D graphene structures, like foams, sponges, or aerogels. These are essentially porous networks of interconnected graphene sheets.
What are they like?
They are incredibly lightweight. Some are lighter than air, yet can be mechanically robust and retain graphene's high electrical conductiveness and enormous surface area.
And what are the applications for those?
Because of the high surface area and conductivity, they're being explored heavily for energy storage, like supercapacitor electrodes, catalysis, environmental remediation, soaking up pollutants, thermal management, and even as porous scaffolds for biomedical applications, like tissue engineering or implants. Researchers have even reported making 3D bilayer graphene structures or observed unusual shapes like box-shaped graphene after cleaving graphite.
And I remember reading about something called pillared graphene. Is that real?
Pillared graphene is mostly a theoretical concept at this point, though there's research trying to make it. The idea is to connect parallel graphene sheets with vertical pillars made of carbon nanotubes.
It's like tiny bridges between the layers.
Exactly, creating a 3D framework. The theoretical predictions suggest such a structure could have unique electronic properties or might be useful for storing hydrogen gas within the pores. But actually synthesizing it in a controlled way is very challenging.
Okay, theoretical for now. Could you actually mold graphene into specific 3D shapes, like press it into a mold?
There's a relatively new technique reported that allows for this, yes. It involved taking flat graphene films, soaking them in a solvent which causes them to swell and become more pliable, almost like wet paper. Then you place the solvent film over a shaped substrate, a former. As the solvent evaporates, the graphene film shrinks and conforms to the intricate shape of the former, basically molding itself into that 3D structure. They've created some quite intricate microstructured shapes this way. Think of it like atomic scale thermoforming or origami.
Tiny, conductive, super strong origami. That's amazing. And finally, what about graphene nanocoils? That sounds strange.
Yeah, this is another really wild one, apparently. Coiled spiral structures of graphene have been found naturally occurring in some types of coal.
Coiled graphene? How does that happen?
It's thought that defects in the hexagonal lattice cause the graphene sheet to curve and eventually spiral up on itself, kind of like a Riemann surface for mathematics.
And what's special about a coil?
Well, if you pass an electrical current through this spiral graphene nanocoil, it should generate a magnetic field, just like a regular electromagnet coil, but at the nanoscale. Computer simulations suggest these could potentially create surprisingly strong magnetic fields, maybe around 1 Tesla, acting as tiny nanoelectromagnets. They might also act as quantum conductors with unusual inductance properties.
Wow, finding nanoelectromagnets in coal. So graphene is clearly this whole diverse family of materials, not just flat sheets. And its properties change dramatically based on its form, structure, and defects. This brings us to the next really big question. How do we actually make all of this stuff? What does the manufacturing landscape look like today?
Right. Making graphene in different forms and quantities is obviously key to realizing all these potential applications. There are broadly 2 main strategies people use: top-down methods and bottom-up methods.
Okay, what's the difference?
Top-down methods generally involve starting with bulk graphite, which is cheap and abundant, and breaking it down or exfoliating it into single or few layers of graphene. Bottom-up methods, on the other hand, involve assembling graphene atom by atom or molecule by molecule, usually starting from smaller carbon-containing precursor molecules, often in gas form.
And the most famous top-down method is the sticky tape one.
Yes, micromechanical cleavage, the Scotch tape method that won the Nobel Prize. It's simple, and it yields very high-quality, pristine flakes. That makes it great for fundamental research and making small prototype devices.
But not for making large amounts.
Exactly. It's not really scalable for mass production. You get tiny, randomly sized flakes.
So what are the more scalable top-down approaches? Using liquids, maybe?
Yes. Liquid phase exfoliation, or LPE, is a major one. This involves using liquids to help peel the layers of graphite apart. You can do this by sonicating, using high-frequency sound waves, or applying strong shear forces to graphite dispersed in certain solvents that match graphene's surface energy. This can produce suspensions containing graphene flakes.
Any other liquid methods?
There's also exfoliation using high-energy interfaces like an oil-water interface. And an interesting approach uses supercritical carbon dioxide, CCO2.
Supercritical CO2, like for decaf coffee?
Sort of, yeah. Under high pressure and temperature, CO2 becomes a supercritical fluid that can slip between the graphite layers, intercalate. When you rapidly release the pressure, the CO2 expands explosively, blowing the layers apart. It's potentially a non-toxic, single-step exfoliation method that can also work for other 2D materials.
Interesting. Can you start with other carbon structures besides graphite?
Yes. People have shown you can chemically unzip or cut open carbon nanotubes lengthwise to form graphene nanoribbons. Or you can even start with fullerenes, those carbon buckyballs. One reported method involves spraying buckyballs at supersonic speeds onto a substrate. The impact apparently causes them to flatten out and bond together into a graphene film.
Spraying buckyballs. Okay. What about chemical synthesis routes? Still top-down.
Some chemical methods start with graphite. The most common is making graphite oxide first, and then reducing it back to reduced graphene oxide, RGO, which we discussed. That initial oxidation step helps exfoliate the graphite into single Jago sheets dispersed in water. Then you reduce it chemically or thermally.
Right, like a DVD burning trick.
Exactly. Or using chemicals like hydrazine or annealing it at high temperatures. There's also a hydrothermal method using sugar, like glucose or fructose, which acts as a reducing agent in hot water to produce stable suspensions of RGO, a potentially greener route.
Sugar again? That's just wild. Any other chemical ways?
You can use electrochemical methods. For example, essentially corroding a graphite electrode in certain molten salts using electricity can produce high-quality, single crystalline graphene nanosheets. Or you can electrochemically exfoliate graphite in specific solvents, sometimes using pulsed voltages to control the properties, or even tracking the exfoliation process using light.
Okay, so lots of ways to break down graphite. What about the bottom-up methods, building it from scratch?
Right, assembling it atom by atom. A major category here is vapor deposition. One important method is the thermal decomposition of silicon carbide, or CX.
How does that work?
You heat a wafer of CX to very high temperatures, over 1100 degrees C, under vacuum or low pressure. At these temperatures, silicon atoms evaporate away from the surface faster than carbon atoms, leaving behind excess carbon atoms that spontaneously arrange themselves into graphene layers directly on the CX surface.
And what's the advantage of that?
This produces what's called epitaxial graphene, meaning it grows in registry with the underlying crystal structure. It can be grown over large wafer areas and is very high quality, often weakly coupled to the SiC, preserving its 2D properties. It's particularly good for applications like metrology, for those quantum resistance standards we mentioned.
Okay. And the other big vapor deposition method?
That would be chemical vapor deposition, or CVD. This is probably the most widely explored method for scalable production of large area graphene films.
How does CVD work?
It typically involves flowing a carbon-containing gas, like methane or acetylene, over a hot metal catalyst surface, usually copper or nickel foil, inside a furnace. The high temperature breaks down the gas molecules, and carbon atoms deposit onto the metal surface and arrange themselves into a continuous graphene sheet.
And you can make large sheets this way?
Yes. CVD can produce graphene films covering areas from square centimeters up to potentially meter scales on foils, or wafer-scale films if grown on catalyst-coated silicon wafers. Researchers have demonstrated growth on standard 100-300 millimeter silicon SiO2 wafers with high monolayer coverage.
So CVD seems like the main contender for making graphene for electronics.
It's certainly one of the most promising for scalable production of high-quality films needed for electronic applications. However, a key challenge with CVD on metals is then transferring that delicate graphene film off the metal catalyst and onto the desired target substrate, like plastic or silicon, without tearing it, wrinkling it, or introducing contamination and defects. That transfer step is still tricky.
Right, the handling challenge again.
Yeah.
Any other interesting ways people are making graphene? The list seems long.
It is. There's the solvent interface trapping method, SITM, which cleverly uses an oil-water interface. Graphene flakes prefer to sit at this interface, acting like a 2D surfactant, which helps exfoliate graphite and allows collection of films. There are also some exotic combustion methods. Even burning magnesium metal in an atmosphere of CO2 can apparently produce carbon nanoparticles that include graphene and few-layer graphene through an exothermic reaction.
Burning metal in CO2.
Wow. There's also supersonic spray deposition, where droplets of reduced graphene oxide solution are accelerated to high speeds. The impact energy on the substrate apparently helps rearrange the atoms into a more flawless graphene structure.
Impact rearranging atoms. And lasers. You mentioned lasers.
Yes, laser-induced graphene, or LIG. It's quite neat. You can take a common polymer film like polyamide, Captain, and just draw on it with a standard CO2 infrared laser engraver. The laser locally heats the polymer to very high temperatures, converting it directly into a porous 3D network of graphene.
Just drawing graphene onto plastic with a laser?
Pretty much. It creates conductive, high-surface area graphene structures directly patterned onto the substrate. It's compatible with roll-to-roll processing, too. You can even make laser-induced graphene fibers, LIGF, this way.
That sounds very useful for flexible devices. What about that trash-to-graphene method?
Ah, yes, flash Joule heating. This is a relatively recent and potentially game-changing technique. It involves passing a very short, intense burst of high electric current through almost any carbon-containing starting material, things like carbon black, coal, petroleum coke, but also food waste, plastic waste, used rubber tires, even pyrolysis ash.
Seriously? Trash.
Yes. This quick electrical pulse heats the material to extremely high temperatures, around 3000 Kelvin, very rapidly for just milliseconds. This intense thermal shock effectively converts the carbon content into turbostratic graphene powder. It's kinetically controlled, bypassing thermodynamically stable forms like graphite.
So potentially a way to upcycle waste into valuable graphene powder? That could be huge.
It really could be if it proves scalable and cost-effective. It produces graphene flakes rather than continuous films, suitable for composites, inks, etc.
Any other methods aimed at electronics?
There's ion implantation, where you accelerate carbon ions and shoot them into thin nickel films on a silicon wafer. With careful control, this can form wafer-scale graphene layers directly on the substrate at relatively low temperatures, around 500 degrees C, potentially avoiding wrinkles or transfer residues.
Lower temperature is good for chip making.
Exactly. And that leads to the ultimate goal for integrating graphene into standard electronics, CMOS-compatible synthesis. This means developing methods to grow graphene directly on the dielectric insulator materials used in computer chips, like silicon dioxide or others, at temperatures low enough, ideally below 500 degrees C, maybe even down to 300 degrees C, so that it doesn't damage other components already on the chip. There are reports of progress using techniques like pressure-assisted solid-state diffusion of carbon through a metal catalyst layer onto the dielectric.
Wow. Okay, so from peeling with tape to sonicating liquids, growing on metal foils, zapping trash with electricity, shooting ions, and integrating directly onto computer chips, the toolbox for making graphene in its various forms is incredibly diverse and seems to be evolving really rapidly.
It really shows the intensity of the research effort worldwide. Scientists are exploring every possible angle to find ways to produce different forms of graphene for different potential uses, constantly trying to balance the quality, the cost, and the scalability needed for real-world impact.
So with all these truly amazing properties we've discussed and this growing toolbox of ways to make it in different forms, where is graphene actually showing up? Where might we, see it or benefit from it in the real world, either now or in the near future? Let's talk applications.
Right. Graphene's unique combination of being basically a transparent, flexible, and highly conductive material, plus all its other quirks, opens up just a vast range of possibilities across many industries.
Like in electronics and displays, that seems like an obvious fit.
Definitely. Its transparency and conductivity make it ideal for things like transparent conductive films, which are needed for touchscreens, flexible displays, and solar cells. The source material even notes that some smartphone products using graphene in their touchscreens are apparently already on the market.
Really? Already out there?
Seems so. It's also being heavily explored for use in flexible displays, more efficient LEDs, potentially better solar cells, and for integrated photonic circuits using light instead of electricity on chips. The ability to grow it on wafers using methods like CVD or those CMOS-compatible approaches we just mentioned is absolutely key for integrating it into next-generation computer chips, maybe for faster transistors or better on-chip interconnects, and also for things like radio frequency electronics.
Okay. What about using its strength and lightness, making things stronger or lighter?
That's another major area, advanced composites. Adding even tiny amounts of graphene or graphene-related materials to polymers, metals, or ceramics can significantly increase their strength, stiffness, toughness, or electrical and thermal conductivity. The source mentions a specific vehicle, the BAC Mono Supercar, which apparently used graphene in its body panels to make it lighter and stronger. It's also being developed for use in high-performance paints and coatings, for example, to provide better anti-corrosion protection. And it can be added as an additive to lubricants, oils, and other functional fluids to improve their performance.
Interesting. And for energy storage or handling heat?
Yes, its high surface area and excellent conductivity are perfect for improving energy storage devices like supercapacitors and batteries. The idea is that graphene electrodes could allow for much faster charging and discharging, higher power density, and potentially longer lifespan.
Faster charging batteries would be nice?
Wouldn't they? And its exceptional thermal conductivity makes it really attractive for thermal management applications, creating heat spreaders or thermal interface materials to pull heat away more effectively from hot electronic components, LEDs, or power systems. It's also being looked at for improving solar cells.
I remember seeing a note about printer powder earlier. That sounded mundane, but maybe important.
Yes, graphene-infused printer powder, or toner, was highlighted in the source as potentially one of the first commercial graphene products to become widely available. Beyond that, graphene is being developed for conductive inks used in printed electronics and as a material for reinforcing filaments used in 3D printing to make stronger or conductive printed objects.
Can it act as a barrier? You mentioned it was impermeable.
Yes. Pristine graphene films can be incredibly effective barriers against the diffusion of gases and liquids, even for tiny atoms like helium. Think about applications like protective coatings, better packaging, or maybe even hydrogen storage tanks.
Okay.
And then there's the strange case of graphene oxide membranes, which are permeable to water but block other things. That paradoxical behavior is being explored for advanced filtration, desalination, or separation technologies.
Right, the water filter idea. What about sensors? That seems like a natural fit, too.
Absolutely. This is a huge potential application area, because every single atom in graphene is on the surface, and its electrical properties are so incredibly sensitive to molecules absorbing onto that surface, it makes for potentially ultra-sensitive detectors.
Detecting what?
Pretty much anything that interacts with the surface, trace amounts of gases in the air, chemical vapors, pollutants in water, even biological molecules like DNA or proteins. This potential translates into developing highly sensitive environmental monitoring sensors, industrial chemical sensors, and maybe most excitingly, biosensors for medical diagnostics or continuous health monitoring through flexible, wearable sensors. Its transparency also makes it suitable for optical sensors.
And those biomedical applications we touched on earlier, like tissue engineering?
Yes, the potential is there. Those 3D graphene scaffolds and foams we discussed could potentially be used to help grow or regenerate tissues, leveraging the studies that showed graphene can promote the growth or differentiation of certain cells, like neurons or stem cells into bone.
But with the safety caveats.
Absolutely. Always keeping in mind the crucial importance of understanding the biocompatibility based on the specific form, size, purity, and surface chemistry of the graphene material being used. It's still an active research area.
Okay. Any really high-precision uses? Anything fundamental?
Yes, actually.
No.
Epitaxial graphene grown on silicon carbide wafers is so electronically uniform and stable that it's being used by national metrology institutes around the world to create incredible accurate quantum resistance standards.
Resistance standards, like for calibrating measurements.
Exactly. These graphene-based standards allow resistance to be measured with extremely high accuracy down to parts per trillion, based on fundamental constants of nature via the quantum Hall effect. It's a very important, though perhaps less flashy, application underpinning precise electrical measurements globally.
That's really fundamental, yeah.
Yeah, it is. And then, of course, there are all the potential applications leveraging the more novel structures we talked about. Those van der Waals heterostructures for creating entirely new types of electronic or photonic devices. The molded 3D graphene shapes for microrobotics or complex components. Graphene fibers for smart textiles or lightweight cables, and maybe even those graphene nanocoils someday becoming useful as ultra-tiny electromagnets or inductors.
And even something as everyday as sports equipment.
Right. The source mentioned it being used in some high-end tennis rackets, presumably added to the composite frame material to increase stiffness or strength without adding much weight, giving players more power or control.
So it's really already spanning everything from the most fundamental physics standards and cutting-edge semiconductor research down to medical possibilities, materials engineering, energy solutions, and even potentially showing up in consumer products like phones or sports gear.
The sheer breadth of potential applications is just astonishing. It's really a testament to that unprecedented combination of extreme properties that graphene possesses. There aren't many materials that tick so many boxes at once.
It's clear graphene is a material that just keeps surprising us, and there's obviously still so much to explore and figure out. What role does computation or simulation play in all this research? Is it important?
Oh, numerical modeling and simulation are absolutely vital tools in graphene research, as they are in most modern material science. Scientists use complex computational methods and equations, things like the Kubo formula mentioned, or models for surface conductivity, or electromagnetic simulations to predict graphene's behavior.
Predict what kind of behavior?
How it conducts electricity or heat under different conditions, how light interacts with it, how different structures like ribbons or dots might perform electronically or optically, how defects affect properties. This allows them to understand experimental results better, and also to design potential devices or applications virtually on the computer before even trying to make them in the lab.
So simulation helps guide and speed up the discovery and engineering process.
Exactly. It allows researchers to test ideas, explore the vast parameter space, and focus experimental efforts much more efficiently. It's an indispensable part of the graphene research ecosystem.
And what about this idea of graphene analogs or artificial graphene? What's that about?
Right, these are other types of physical systems, usually two-dimensional, that aren't actually made of carbon atoms in a honeycomb lattice, but they are engineered to mimic graphene's unique electronic properties, particularly that strange behavior near the Dirac points, where particles act massless.
So not graphene, but acts like it. Why do that?
Researchers create these analogs, sometimes called artificial graphene, using different building blocks, maybe photons moving in specially designed optical lattices, or ultra-cold atoms trapped in optical potentials, or electrons in other semiconductor structures. They do this because these artificial systems can sometimes be easier to build, control, and probe experimentally than actual graphene samples.
So they provide simpler, more controllable test beds to study the fundamental physics principles that make graphene itself so special, like the effects of the honeycomb lattice structure.
That's exactly right. They offer alternative platforms to gain deeper insights into the unique physics driven by that specific lattice symmetry and topology, without necessarily dealing with all the material complexities of real graphene.
This has been an incredible deep dive into the truly fascinating world of graphene. We've journeyed all the way from its theoretical origins decades ago and that famous, almost accidental discovery with sticky tape.
To exploring just an astonishing array of properties that really seem to push the boundaries of physics and material science. We've seen how this single layer of carbon can be, simultaneously, the strongest material known at its scale, incredibly light and flexible, uniquely transparent yet visible.
How it conducts electricity better than silver, conducts heat better than diamond, and exhibits these mind-bending quantum behaviors, acting like a zero-gap semiconductor with effectively massless charge carriers showing weird quantum Hall effects.
And we've covered the incredibly diverse and rapidly evolving ways researchers are figuring out how to actually make it from simple peeling to complex chemical vapor deposition, laser writing, and even zapping trash, and how they're shaping it into different forms beyond just flat sheets, ribbons, dots, oxides, fibers, 3D foams, and more.
Which, in turn, opens up this vast landscape of potential applications across nearly every field imaginable, from next-generation electronics, photonics, and energy storage, to stronger materials, advanced sensors, biomedical engineering, and even fundamental metrology.
It's clearly a material just brimming with complexity, too. We've touched on the ongoing debates about how defects and grain boundaries really affect its properties in large-scale samples, the puzzles that remain like its minimum conductivity near the Dirac point, and the critical work still being done to fully understand its long-term stability and its interactions with the environment or biological systems.
It really highlights how much there is still to learn and unlock about this seemingly simple single sheet of carbon atoms. It's definitely not a solved problem yet.
Absolutely. And this perhaps leads us with a fascinating thought for you, our listeners, to consider. Given graphene's truly unprecedented and unique combination of properties being the strongest, thinnest, most conductive material, while also displaying such unusual quantum, optical, thermal, and chemical behaviors, what completely new technologies or solutions might it enable in the coming years or decades? Things that were simply impossible, maybe even unimaginable, with any materials we had before. How might this single layer of carbon atoms ultimately reshape our future in ways we can't even fully envision yet?
Welcome to the Deep Dive. Today we're really getting into a heavy topic, one that shapes so much. Racism. We've got quite a pile of source material here, historical stuff, definitions, examples from all over. And our mission really is to go through these sources with you, pull out the key takeaways, kind of a shortcut, to understanding how these materials present this complex subject. Let's jump in.
Yeah, it's definitely a topic with a lot of weight. Very sensitive. And just to be clear, as we dive in, we're really sticking to what the source material says. Definitions, history, examples, all as presented in these documents we have. It's about understanding the sources themselves, not adding our own opinions or anything outside them.
Okay, makes sense. So let's start right there with the definitions. How do the sources actually define racism from the get-go? What's the basic idea?
Well, they generally start with the belief that different human groups have distinct behavioral traits, and that these are tied to inherited features. And crucially, that this leads to ranking these groups, one race or ethnicity seen as superior. It also covers the prejudice, the discrimination, the antagonism that follows from that belief.
Right, the belief leading to action.
Exactly. And the sources also mention how modern ideas link it more to social perceptions, maybe of biological difference, even if those differences aren't scientifically real in the way people think. And these perceptions can feed into actions, practices, even political systems that rank people.
That link is key. Now, the sources mention attempts to, legitimize these ideas with scientific racism. What do the materials say about that?
Yes. The sources are very direct about this. They explain that historically, fields like physical anthropology, anthropometry, were used to try and justify racism. But, and this is crucial, the materials state very clearly that these attempts have been thoroughly debunked. Completely unfounded scientifically. Those disciplines in that context are discredited now. They even bring up the Human Genome Project, pointing out it found no real genetic basis for these racial categories people use, really undermines those old scientific claims.
So the science just isn't there, according to the sources. Okay. What about the terms race and ethnicity? The source material notes they're distinct in modern social science, but often used interchangeably in practice.
That's right. The sources clarify that while academics today might draw sharp lines, historically and, in everyday talk, they've often blurred together. So because of that history, the words racism and racial discrimination often get used when talking about discrimination based on ethnicity or culture, even if it's not strictly about race in that old biological sense. And they point to the UN Convention on the Elimination of All Forms of Racial Discrimination. It basically says, for its purposes, there's no distinction between racial and ethnic discrimination. And it declares any idea of racial superiority is scientifically false, morally wrong, socially unjust, the whole package.
Interesting how the language itself shows that evolution or maybe confusion. Okay, let's step back. The sources frame racism as a relatively modern idea, really developing in certain historical periods. Where do they trace its roots?
Yeah, they really focus on the European age of imperialism. That's presented as a key period where modern racism evolved. It was shaped by capitalism, and the sources identified as a major driving force behind the Atlantic slave trade specifically.
A driving force behind it, not just a justification after.
That's how the sources frame it, yes, a major driver. And then they trace its impact forward racial segregation in the U.S., apartheid in South Africa. They also connect it to several genocides, mentioned the Holocaust, the Armenian and Rwandan genocides, the genocide of Serbs, and also to colonial projects, like European colonization generally, and even population transfers in the Soviet Union. And, importantly, the sources make a point of saying indigenous peoples often faced, and still face, racist attitudes described in the material.
The sources mention the word racism popping up around 1902, becoming common in the 1930s, but the concept existed before the word, right?
Oh, absolutely. The sources say it's generally agreed the concept is older than the term. But they also caution there isn't one single definition everyone agrees on across all time. Which is why, according to the material, some scholars prefer using racisms in the plural, to capture all the different ways it's looked across history in different places. It's a subtle but important point the sources make.
That idea of racisms makes sense. Okay, let's go even further back then. What about antiquity? The sources touch on things like ethnocentrism, prejudices before modern racism. What's the distinction there?
Right, they bring up examples like Aristotle, his views on Greeks versus barbarians, where Greeks were naturally free, barbarians naturally slaves. But the sources are careful here. They say Aristotle wasn't basing this on race as we think of it. His distinctions seem more about the soul, or maybe culture, not inherited biology. That idea of hereditary inferiority linked to race wasn't really there yet, according to the sources.
So different from modern racism.
Yes. They contrast it with ethnocentrism, like ancient Hebrews calling non-Hebrews Gentiles, or Greek is calling non-Greeks barbarians. The sources argue that's more about group identity and perceived cultural differences as ethnocentrism, not quite the hierarchical system based on race that developed later.
Okay. What about medieval examples? The sources mention Arab writers and the Spanish limpieza de sangre.
Yeah, they explore those as possible precursors or maybe just different forms of discrimination. Some scholars, the sources note, see ancient anti-Jewish policies as maybe early racism. But others disagree, arguing it was more about suppressing a religious group that wouldn't conform, not a racial thing per se. And the Arab writers? The sources say while the Quran itself doesn't show racial prejudice, ethnocentric biases did develop later among some Arabs, influenced by conquests, the slave trade, philosophical ideas maybe. This apparently led to some discrimination against black people by the 8th century, although the sources also say some Arab authors argued against this prejudice.
And the Spanish example? Limpieza de sangre.
Cleanliness of blood, right. The sources explain the system came about after Moors and Jews were expelled from Spain. It was supposedly about making sure old Christians weren't related to recent converts who might secretly practice their old religion. But the sources give it a sharp edge, calling it, and I'm quoting roughly here, Spain's reminder that aristocracy's refined history carries the less refined trace of racism, unquote. And they note this concept spread to the Americas, feeding into the caste systems there based on how much European ancestry someone supposedly had.
Wow, that really traces a complex evolution. Okay, moving forward, the sources outline lots of different ways racism shows up in society. What are some of the key aspects they describe?
They cover quite a few. One is aversive racism. This is described as more subtle, often unconscious, not overt hate, but like negative feelings or avoidance toward minority groups. Even people who genuinely believe they're egalitarian might show it, the sources say. It can lead to unconscious shifts in behavior.
So it's hidden even from the person themselves sometimes.
That's the idea presented, yes. Then there's color blindness. The sources describe this as trying to ignore race altogether. Seems positive on the surface, maybe, but the sources argue this approach can actually perpetuate inequality without meaning to. By ignoring real racial disparities, it kind of defaults to the dominant group, often white people, as the norm. This can make the biases and discrimination others face sort of invisible. That's a key argument in the materials.
Okay, that's a nuanced point. What else?
Cultural racism. This is defined as the belief that one culture's stuff, language, traditions, values is superior to others. The sources link it to xenophobia sometimes. Then there's economic racism. The sources connect historical discrimination to ongoing economic gaps between groups today. Past racism creates disadvantages in education, wealth, opportunities that carry over generations. And they give some really specific examples of how bias gets embedded. Things like color film being calibrated mainly for white skin tones, or automatic soap dispensers not always sensing darker skin, even facial recognition having trouble with darker faces.
Wow, everyday technology.
Exactly. Shows how bias can be built right in. Then, institutional racism. This is discrimination by big organizations, government, companies, schools. The sources credit Stokely Carmichael with the term and mention his definition about the collective failure of an organization to serve people properly because of race or ethnicity. The emphasis in the sources is that this isn't just about individual prejudice. It's about power structures, policies, practices that maintain dominance and actively discriminate.
So it's baked into the system itself.
That's the idea. The sources also mention othering. This is the process of defining a group as fundamentally different, separate from the norm. Often relies on stereotypes, imagined differences. The example used is how European colonialism constructed Orientals as the exotic, different other.
Okay. And straightforward discrimination and segregation.
Yeah, the sources define racial discrimination simply as discrimination based on race, and racial segregation is separating groups in daily life. Even if it's illegal, the sources note, it can persist through social norms like historical separate but equal things or ongoing issues in housing.
Got it. What about supremacism?
That's the belief one race is inherently superior. The sources give white supremacy as a major example, used to justify colonialism, think white man's burden. They include some pretty disturbing quotes and texts from the material, like from Thomas Jefferson or L. Frank Baum, and even the Declaration of Independence, showing dehumanizing views of Native Americans. But the sources also mention that attitudes reflecting Black, Arab, or East Asian supremacy are also discussed in the materials.
So it's not limited to one group believing it.
According to the sources, no. Finally, they touch on subconscious biases, drawing on recent social psychology. Research mentioned suggests even people who consciously reject racism might still have unconscious race-based biases affecting their judgments. The sources differentiate this from, like, full-blown conscious racism, but note the impact can still be discriminatory, even if unintended. They also mentioned some studies looking at how these biases might be learned early on, maybe related to peer groups or even things like threat perception in the brain.
That's a really wide range. The sources cover conscious beliefs, systemic issues, tech bias, unconscious stuff. Okay, let's focus on the 20th century. The materials give some stark examples of state-sponsored racism, Nazi Germany and the U.S.
Yes, the sources go into chilling detail. For Nazi Germany, they explain the ideology of the Aryan master race, how this justified expanding territory and enslaving or killing groups deemed inferior. Romani people, people of color, Slavs, and especially Jewish people, who the sources say were placed at the absolute bottom, seen as inhuman and targeted for extermination in the Holocaust. The materials even add a grim detail. Nazi policy towards Slavs apparently shifted a bit during the war, but only due to manpower needs.
Horrifying. And the U.S. connection.
This is really striking in the sources. They describe German legal experts in the 1930s actually looking to the U.S. for models of institutional racism. They explicitly mention U.S. citizenship laws based on race and anti-miscegenation laws as influencing the Nazis' own Nuremberg laws. The sources even quote Hitler's Mein Kampf, where he apparently expressed admiration for how the U.S. treated coloreds and expanded westward against Native Americans. That parallel, drawn from the source material, is deeply disturbing.
It really is. And shifting to the U.S. itself, what more do the sources say about segregation and its legacy?
Well, they portray white supremacy as dominant from the founding up until the Civil Rights Movement forced legal changes. They mention early laws like the 1790 Naturalization Act limiting citizenship to whites and court cases upholding that. It wasn't until much later, like the 1965 Immigration Act, that those explicitly race-based citizenship rules were fully dismantled. The sources state clearly that legal segregation existed right up into the 1960s.
Ending with the Civil Rights Act of '64.
Right. But, the sources argue, de facto separation and discrimination didn't just vanish. They persist, according to the materials, in things like unequal access to housing, education, resources, or biased treatment by authorities.
So the legal structure changed, but the effects linger. Beyond the US and Germany, the sources paint a global picture of contemporary racism too, right?
Oh, definitely. They provide a whole list of examples from around the world to show how widespread and varied it is. Things like a hate speech case involving Julius Malema in South Africa. Really disturbing reports cited from the Congo War about pygmy people being hunted. A UN report mentioned condemning Botswana's treatment of the Bushmen. Accusations of racism against Robert Mugabe towards white people. Anti-African student riots and debates about racism in China connected to a specific case, Lu Jing.
It really is global.
Yeah, the list goes on. Expulsion of black Mauritanians, slavery and abuse reported during the Sudan Civil War, the Darfur conflict described in the sources as having racial dimensions, deportations of Arabs in Niger, anti-Chinese riots in Indonesia, Papua New Guinea, attacks on Indo-Fijians, and the sources talk about deep-seated racial divisions or state policies seen as racist in places like Guyana, Malaysia, mentioning the Bumipundra policies, specifically Trinidad and Tobago, Madagascar, South Africa, and the violence against Rohingya Muslims in Myanmar, described in the source material as fueled by racist hatred. It's a stark reminder from the sources that this isn't confined to one region or one form.
That sheer breadth is sobering. The sources also include some recent data, like a UK survey.
Yes, they mention a specific 2023 University of Cambridge survey. It polled black people in Britain. The findings cited are pretty stark, like 88% reported facing racial discrimination at work. 79% felt police unfairly targeted black people with stop and search. 80% saw racial discrimination in education as the biggest barrier for young black students. It just provides a very concrete, recent snapshot from the sources for one country.
Okay, so after covering all these problems, the sources also discuss efforts to fight back anti-racism. What do they say about that?
They define anti-racism pretty broadly, according to the sources. It covers beliefs, actions, academic work, social movements, government policies, anything aimed at opposing racism. The goal described is creating an egalitarian society, free from race-based discrimination. Examples given include the U.S. Civil Rights Movement, the anti-apartheid movement in South Africa, and Black Lives Matter. The sources also note that nonviolent resistance is often part of the strategy. And on the policy side, things like hate crime laws, affirmative action, and bans on racist speech are mentioned as anti-racist measures.
That makes sense. Now, one more concept the source material addresses is reverse racism. How do they define that, and what's the perspective offered?
Right. The sources explain reverse racism as a term usually used to describe discrimination or hostility from a minority group towards a dominant group, sometimes implying minorities are being unfairly favored. They note it comes up a lot in debates, especially in the U.S., about policies like affirmative action, which are designed to address past inequality.
And the source's take on it?
Well, the sources present a view of many experts who argue reverse racism is basically a myth. The reasoning provided in the materials is this. While individuals and minority groups can certainly hold prejudices, they generally lack the widespread political and economic power to systematically oppress the dominant group. So if you use a definition of racism that includes that power dynamic, like the prejudice plus power idea mentioned in the sources, then discrimination from minority towards majority doesn't really fit the bill, according to this perspective. The sources also briefly allude to related academic discussions, like the tension between formal equality and substantive equality, or arguments about whether policies like affirmative action violate formal equal opportunity.
Okay, so pulling this all together, this dive into the source material really paints a picture, doesn't it? Racism as this deeply rooted, evolving thing with a complex history, manifesting in so many ways overt policies, subtle biases, systemic issues, even in tech. And the sources show it's global, multifaceted, but also that there are ongoing efforts to challenge it.
Yeah, what really stands out from just reading these sources is that tension they present. You have these formal efforts, like the UN trying to define and outlaw racism, but then you have all these examples in the material showing how discrimination keeps popping up, sometimes in really sneaky ways, built into systems we use every day, like that film or facial recognition example. It's quite the contrast.
Right. It definitely underscores, based on these sources, that understanding racism isn't just about history lessons or obvious prejudice. It's about looking at structures, policies, maybe even our own unconscious thoughts, like that psychology research suggests. So Here's something to leave you thinking about, drawing directly from the material we've discussed. The sources showed us these ongoing debates among scholars using racisms maybe, arguing about the prejudice plus power definition, the whole reverse racism discussion. Given that complexity, that long history, and all the varied forms presented in the source material, how does understanding that complexity as laid out in these sources maybe change how you think about the challenge of actually addressing racism today?
Welcome to the Deep Dive.
Great to be here.
Today, we're really diving into something you brought to us, this concept of habeas corpus.
That's right. And we've gathered quite a bit of material sources looking at its history, what it actually means, and how it plays out across the globe.
Yeah, quite a stack. Our mission today, then, is to unpack this really fundamental legal idea. It gets called the Great Writ of Liberty, doesn't it?
It does. And we want to figure out why. Why that label? What does it actually do that makes it so important?
And the name itself is kind of a clue, right?
Yeah.
Habeas corpus, Latin.
Exactly. Let's break it down. Habeas, that means you should have, and corpus, body.
You should have the body.
Precisely. The fuller phrase you sometimes see is habeas corpus ad subjudiendum.
Okay.
Which basically means that you have the person before us so we can subject the case to examination.
So it's literally a court command. Bring the person here.
That's the core of it. It's a specific type of court action. It's how someone challenges being detained or, imprisoned unlawfully.
And it's aimed at the person actually holding the prisoner, not the judge who ordered it or anything.
Right. It's addressed to the custodian, the jailer, maybe the warden, whoever has physical control of the person. And it demands they bring that person physically before the court.
Okay, bring the body, and then what?
Then the custodian has to justify the detention. They have to show the court their legal basis, their proof of authority for holding that individual.
And if they can't, if the authority isn't there or it's flawed,
then the court orders the prisoner released. Simple as that. It's a direct challenge to the power to detain someone, whether that power is the state's or even sometimes a private person's.
Okay, so that's the basic idea. Let's get into the nuts and bolts a bit more. How does this work procedurally? The sources call it an extraordinary writ. What makes it different from, say, filing a normal lawsuit?
Yeah, that's a really key point. It's different because of where the burden of proof lies. In most civil cases, the person bringing the lawsuit, the plaintiff, has to prove their case, right?
Right. They have to convince the judge.
With habeas corpus, it's flipped. It operates on what's often called a presumption of non-authority.
Presumption of non-authority. That sounds important.
It's huge. It means the official holding the person they're called, the respondent, they start from a position of having no presumed right to hold that person. They have to actively prove to the court that the detention is lawful.
So the person asking for the writ doesn't have to prove innocence or anything?
Not initially. The petitioner, and this can be the prisoner or someone else acting for them, basically wins if the official fails to show proper legal authority for the detention. The responsibility is squarely on the custodian.
Wow. So it's not prove you're held illegally, it's prove you're holding him legally.
Exactly. That's the check. It's meant to stop people being locked up arbitrarily or, disappeared without legal reason.
Are there limits? Can anyone just demand this for anyone?
There are some practicalities. The person filing usually needs to show what's called a prima facie case.
Prima facie?
Yeah, just enough credible information to suggest the detention might be unlawful, enough to get the court's attention. And famously, the writ can be suspended.
Ah, right. You hear about that?
Usually only in extreme circumstances, like declared wars or rebellions. And even then, that power to suspend is often heavily restricted by constitutions and fiercely debated.
Okay, let's shift to the history. Because this goes way back, doesn't it? People often link it straight to Magna Carta, 1215, but the sources suggest it's older.
That's a common thought, but yeah, the roots are deeper. While Magna Carta is incredibly significant, similar legal ideas, writs demanding someone be brought to court, existed even earlier. Things like the Assize of Clarendon in 1166 were steps along the way.
But Magna Carta definitely cemented the principle.
Oh, absolutely. Right. Clause 39 is the famous one. No free man shall be imprisoned, except by the lawful judgment of his peers or by the law of the land.
The law of the land bit seems key.
It is. But Clause 38 is also really interesting in this context. It says, Basically, that officials can't start proceedings just on their own say-so. They need reliable witnesses first.
So evidence before you arrest someone.
Exactly. It implies you need a basis, some evidence, before you make an arrest or bring charges. An arrest without that basis wouldn't be considered lawful under that framework. That sets the stage for challenging detention based on lack of lawful grounds.
So when does the actual term habeas corpus ad subjiciendum show up?
The famous jurist William Blackstone points to 1305, during Edward VI's reign, as the first recorded use of that specific Latin phrase.
1305. Okay.
Though, like we said, similar court orders existed before then, Blackstone framed it, interestingly, as the king's right to know why any of his subjects were being detained.
Like the king checking up on his own officials.
Sort of, protecting the king's interest in his subjects, which over time became more about protecting the subject's right directly.
Okay, fast forward a bit. The sources highlight the Habeas Corpus Act of 1679 in England as a really big moment.
Yeah.
What led to that?
Well, there had been some court rulings that kind of weakened the writ's power. An earlier act in 1640 had already pushed back against the idea that the king could just order someone detained without question. The 1679 act really solidified things, made the procedure stronger.
And the political climate was
Yeah.
intense.
It was passed right in the middle of a big showdown between King Charles II and Parliament. Parliament was dominated by the Whigs, who were pretty worried the king might start locking up his political opponents.
So they passed the act to protect themselves, partly.
That was definitely a major motivation. In fact, that specific parliament became known as the Habeas Corpus Parliament.
Wow, named right after the act. That says a lot.
It really does. And besides checking the king, the act also limited the power of another court, the Court of Chancery, to use its equity rules to undermine common law decisions, including release orders.
Did the use of the writ broaden out from just challenging the crown?
Yes, absolutely. The sources show it started being used against private individuals, too. Say, if someone was holding another person unlawfully, maybe in a family dispute, or even forcing them to work.
Like the Somerset case in 1772. That's mentioned as a landmark.
A huge one. James Somerset was an enslaved black man brought to England. The writ was used to challenge his owner's claim to hold him and forcibly take him out of England. The court ruled he had to be freed.
And there's that famous quote.
That the air of England was too pure for slavery.
Powerful stuff. The sources clarify it was likely the lawyers arguing the case who used the phrase, citing an earlier precedent rather than the judge himself, but the impact via habeas corpus was undeniable.
What about wartime uses? You mentioned suspensions, but was it ever used during conflicts?
Yes, historically it was used, for instance, during the 7 Years' War. People would use it to challenge impressment, being forced into the Navy or Army.
Right, forced service.
And later acts, like one in 1816, made some adjustments and clarified its reach.
Okay, back to the suspension point. How has that worked in practice in England? It has been suspended, yes, several times, especially in the 18th and 19th centuries when there was significant unrest. But it's important to get the nuance the sources point out for more modern times.
Okay.
During things like World War I, World War II, or the Troubles in Northern Ireland, specific laws were sometimes passed allowing detention without trial in certain circumstances. Now, technically, habeas corpus was still available. A detainee could still file.
But would it work?
Probably not if the detention was clearly authorized by that specific act of Parliament. Remember, habeas corpus asks, is the detention lawful according to the current law? If Parliament passes a law saying detention X is lawful under conditions Y, and those conditions are met, the writ might just confirm that.
Ah, I see. So it enforces the law but doesn't necessarily challenge the law itself.
Yeah. Exactly. It's primarily a check on executive power acting under the law, not usually a direct challenge to the legislature's power to make that law. Although the Human Rights Act 1998 in the UK does allow courts to declare laws incompatible with human rights standards, but that's a separate step requiring government action. It's not the writ doing that directly.
Okay, that distinction is important. How about today in England? Do they still physically bring the body to court every time?
The modern practice is a bit more streamlined. The core principle is the same, but often there's an initial hearing first, with lawyers for both sides arguing the legality. A judge might order release or bail right then, without the prisoner having to be physically present at that stage. Sometimes a different process called judicial review is used instead.
Makes sense. More efficient.
But the writ itself is definitely still alive and kicking. The UK Supreme Court confirmed its availability as recently as 2012, even for someone captured by British forces overseas in Afghanistan.
So the core idea persists. Now, this is where I think it gets really interesting. This isn't just an English thing, is it? The sources point to similar ideas popping up elsewhere.
Absolutely not just English. And that's maybe the most striking thing. This fundamental worry about being locked up without reason and the need for some way to challenge it, that's appeared in many different legal traditions.
Almost like a universal legal instinct.
You could certainly see it that way. The sources give some amazing examples that actually predate or developed totally separately from the English common law tradition.
Like where?
Well, look at the Crown of Aragon in what's now Spain. They had something called the Manifestación de Personas, and this was codified way back in 1325.
1325. Wow, that's long before the 1679 English Act.
Definitely. And it worked differently, too. There was the special official, the Justicia de Aragon.
The Justicia.
Yeah. This figure had the power to demand that authorities hand over anyone being prosecuted. The Justicia would then take custody, not necessarily to jail them, but to protect their rights, prevent abuse, ensure a fair process.
So like an independent protector stepping in.
Exactly. And the Justicia could actually refuse to return the person to the original authorities if they thought the trial or proceedings were unjust. People under manifestation were apparently held in pretty mild conditions. There's a famous case involving Antonio Perez in 1590 where this was used against the king's wishes.
That's a really different model, putting custody with an independent figure. Fascinating. Any others?
Poland provides another really early example. Back in 1430, they established a principle called Neminem captivabimus nisi ire victim.
Okay, Latin again. What's that mean?
We will not imprison anyone except if convicted by law.
That sounds very much like the core idea. No imprisonment without legal conviction.
Pretty much nails it right. It started with the nobility, but was later extended to townspeople in 1791. So for its time, it protected a large chunk of the population against arbitrary arrest with clear legal backing.
So these ideas were definitely bubbling up independently. How did the principles spread or get adopted in more modern times?
Well, many countries inherited it through the English common law system. Think of the United States, Canada, India, Ireland, New Zealand, Pakistan. In these places, habeas corpus, or a very direct equivalent, is baked into their legal systems.
How so in the U.S.?
It's right there in the Constitution. Article 1, Section 9, the suspension clause. It explicitly says the writ can't be suspended except during rebellion or invasion if public safety demands it. It's treated as a civil case used to challenge all kinds of custody, pretrial, post-conviction, even immigration detention.
And its suspension has been controversial in the U.S.
Oh, absolutely. Lincoln during the Civil War, FDR during World War II, and more recently, the Supreme Court battles over access for Guantanamo Bay detainees, like in Boumediene v. Bush, which struck down attempts to block it. It's a recurring point of tension.
How about Canada?
Similar story. Inherited tradition, but also explicitly guaranteed in their Charter of Rights and Freedoms, Section 10C, guarantees the right to have detention reviewed and be released if it's unlawful. Their courts have established tests, like in the Keela case, requiring authorities to prove lawfulness once a valid question is raised.
And India. You mentioned them.
Yes, India's Supreme Court and High Courts have the power to issue these writs. The sources mention their constitution framers deliberately put it in the Constitution itself, worried that future legislatures might try to weaken it.
Smart.
And interestingly, Indian courts seem to have expanded its use, allowing almost anyone to petition for someone else, applying it against private detention too, sometimes citing those old English cases like Somerset.
So taking the principle and maybe running with it even further.
Seems that way in some applications, based on the examples given.
What about countries without that English common law background? Say, in continental Europe.
Right, civil law systems. Places like France, Germany, Italy, Spain, Portugal. They don't typically use the term habeas corpus, but they absolutely have equivalent strong protections built into their systems.
How do they achieve the same goal?
Often through constitutional guarantees and detailed rules within their criminal procedure codes. Things like strict requirements for a judge to approve detention, very short time limits, often 24 or 48 hours to bring someone before a judge after arrest, and clear processes for challenging the legality or conditions of detention.
So Germany might require seeing a judge within a day.
Exactly. Italy has specific review courts, the Tribunale del Riesame, to challenge detention orders. France emphasizes judicial authority over liberty and speedy decisions, building on principles from their 1789 Declaration, which, interestingly, Thomas Jefferson had a hand in drafting.
So the legal plumbing looks different, maybe as part of the standard criminal process rather than a special writ, but the outcome judicial review of detention is the same.
That's the core idea, yes. To ensure detention requires prompt, lawful justification reviewed by a court. Spain, for instance, building on its own history like the manifestation, actually passed a specific law of habeas corpus in 1984. It allows detainees, or even third parties, to demand an appearance before a judge within 24 hours if they think the detention lacks authority, violates rights, or involves mistreatment.
It really is striking how this idea keeps surfacing across such different legal cultures.
It really is, and the list goes on. Malaysia's constitution has a similar guarantee. New Zealand uses it against private parties. There's a case mentioned about challenging a family kidnapping. Pakistan's courts use it to check not just lawfulness, but also if detention was carried out in bad faith.
Bad faith,
Yeah.
interesting.
Portugal's constitution allows any citizen with political rights to apply for it. The Philippines guarantees it, though with a suspension clause like the U.S., which has been invoked during periods of conflict, most recently in Mindanao. Even Scotland, part of the UK but with its own legal system, has an equivalent law from 1701. And Taiwan's constitution guarantees it, requiring appearance within 24 hours and release if detention is illegal.
Okay. So, wrapping this all up, what's the big takeaway from this deep dive?
I think it shows that this principle, the right to challenge your detention and demand the state or whoever's holding you show their legal cards, it's not just some quirky old English thing. It seems to be a response to a really fundamental human concern, one that different societies have found ways to address legally over centuries.
It feels like a cornerstone of individual liberty, doesn't it?
Yeah.
A way to make sure power, whether state or private, can't just make people disappear or hold them indefinitely without answering to the law and the courts.
Right. It forces the issue into the open, show the body, show the authority.
We've really traced this idea from places like medieval England and Aragon, through acts of parliament, key court battles, right up to modern constitutions across the Americas, Europe, Asia, all circling this core concept. Bring the person before the court, justify holding them.
Absolutely. And maybe a final thought to leave people with, drawing on the implications in the sources. You often hear the phrase, justice delayed is justice denied. How does the whole point of habeas corpus demanding that speedy review of detention directly connect to that idea?
Good question.
And maybe what does it mean for liberty, for justice itself, when that process gets slowed down or complicated or, in those extreme cases, suspended altogether?
Something to think about. That was our deep dive into habeas corpus. Hope you found that journey through law and history as fascinating as we did.